So welcome back to this third lecture on this module, control volume analysis of fluid systems. Okay, this is the application of basically what we have learned in the previous lecture. Okay, so in previous lecture we identified about the Reynolds transport theorem. Correct. So Reynolds transport theorem actually connects the rate of change of property of a system to that of a control volume. We have studied this. Okay, so now let us see what let us apply basically the equations what we have learned actually in previous case. Okay, so let us see here. Oh, just a minute, I think there is some issue. Fine then. So in this case I'm going to talk about only two things, which is very important things. Of course, if you see applications of linear momentum equation and also this applications of the angular momentum equation. Of course, continuity we have seen a lot of times. Even in differential analysis we have talked about the mass conservation a lot of times. Okay, so let us suppose if for example if there is some flow, for example, then we have seen how to calculate the average velocities. Okay, we have seen if some fluid is emitted all over the circumference of the pipe, then what is the inlet and outlet velocities are known to you, then what is the emittance velocity. We have talked about all these things basically. Okay, so now let us have a quick revision of what we have learned, and let us try to apply these equations to the control volumes. Okay, so let us try to understand this. So we have talked about this RTT, Reynolds transport theorem. So this Reynolds transport theorem tells you that if B is any property of the system, so dB by dt of this system is actually equal to dou by dt of integral over the control volume beta times rho dV is what you have, plus over the control surface beta times of rho v relative velocity bar dot n cap ds. Okay, so this is what we have learned. Correct. So this is the Reynolds transport theorem equation, mathematical equation of the Reynolds transport theorem, where this is the property change of the control volume and this is basically the net efflux which is causing the control surface of any control volume. Okay, so we have seen if you apply this equation to various things, we have seen for mass, if you apply this, we have seen that the equation gets converted to dou by dou t or dou rho by dou t plus divergence of, or generally this is in another form. So if you see, we have seen under steady state. Okay, so under steady states, let us write under steady states, for example, under steady states, we have seen under steady state basically this term is actually 0. Correct. So this term which is here, this term will be a big 0. Correct, because rate of change of this quantity with respect to time is 0. We have seen. So in case of mass, we have seen cyclic integral over the complete control surface rho times of v bar dot n cap dA. So this is equal to 0 is what we have seen. It is dot product, so this is a scalar quantity. In second case, we have seen net force acting on the fluid. Net force acting on the fluid is equal to control surface momentum vector, which is v r bar times this rho v bar dot n cap dA. Okay, so n cap dA is what we have seen. This is basically in the case of net force acting on the fluid. So this is the linear momentum equation which we have seen. Linear momentum equation which we have actually seen in this case. Okay, so linear momentum equation. And now if you see the third case, we have seen net torque acting on the fluid is equal to this integral over the control surface r bar cos v bar times v relative cos this rho v r bar cos n cap ds. Okay, so this is what you have basically here. Okay, so this is the ds. This is the effective mass fluid. That's what we mean. Okay, so this is the effective mass fluid that actually flows to the control volume. So these are the three equations, and we have seen this equation is the angular momentum equation. Angular momentum equation. Okay, so this is angular momentum equation. Angular momentum equation. Okay, so we have talked about this angular momentum equation, linear momentum equation. Now let us apply. Of course, we have seen a lot of applications of this continuity equation. See, what is the meaning of this? Total mass which is causing the control volume is actually 0. Correct. The meaning of this, let us suppose you have a pipe, for example. Okay, means you see here, for example, applications of linear momentum equation. Before that, let me anyhow talk one word about this mass momentum also. So this is mass conservation equation. So basically this is conservation of mass. Conservation of mass. Correct? So this is conservation of mass. Now try to understand something. Look, let us suppose if this V bar and this n cap both are actually collinear, means basically let us suppose the angle between them is 0. Meaning of that is basically this dA and this V bar are perpendicular to each other. Correct? Because n cap is the vector which is perpendicular to dA. So if V bar is also perpendicular to dA, then definitely the angle between these two is actually 0 degrees. So this equation gets converted to OVdA. Look, conservation of mass, let us apply first of all. If you talk about the conservation of mass, for example, we have done lot of examples in case of differential analysis, but once again let us see. I want to show you one thing which is generally used in our case. Look, let us suppose if there is a pipe, for example. Okay, let us suppose if there is a pipe. So this pipe has a circular cross section, for example, let us say here. So at this section we have a section here, and here also we have a section. Okay, so now this section is actually 1 or inlet section, let us call, and this is outlet, for example. Okay, now your job is to know what is the mass fluid. So let us suppose if there is some fluid which is flowing in this pipe, and your point of observation is what's happening in this region of the pipe. Okay, so the pipe is actually somewhere here. Let us suppose you have connected some manometer, whatever you have connected. Your focus is on this volume of the pipe, for example. Okay, so let us suppose this is of some length L. Then to understand what's happening in this pipe, look, in this case what happens is, if you want to apply control, this continuity, steady state, let us suppose if you have a steady state in this case, then when you have the steady state, integral over the control surface rho times of V bar dot n cap dA, this has to be 0. Correct? This has to be 0. Now try to understand this. How this equation is 0? We know this equation is 0. So if this equation is 0, let us see what happens. Okay, so look, this total control surface can be identified as two parts. What are they? One is this area, one is this area which is available at the inlet, this area which is available at the outlet, and this total area, this is the control surface. Correct? If you see, this total surface of this cylinder is the control surface. Now fluid actually enters at one point and leaves at one point. There is no medium in which the fluid can actually go in between. Correct? You see, the fluid cannot escape because this is some pipeline. Okay, so let us suppose I want to denote this as a pipe, for example. So let us suppose if this is some pipeline, for example. Okay, so this is actually a pipe. Okay, so if this is a pipe, then we have one fluid inlet and one fluid outlet. Correct? So at this point, if you see, outward surface n cap is in this direction. Try to understand, guys, it's very important actually. Okay, so n cap is in this direction to this surface, and also you have one more thing, velocity is in this particular direction. So the angle between these two is exactly how much? 180 degrees. Correct? So V in, for example. Similarly here n cap is exactly outward normal, means if you take the surface, then the surface has the outward normal in this direction. This is the n cap direction here, and also the velocity vector at this location is in this direction. So they are in the same directions. Now this is in the same directions. Now try to understand one thing. If I call this inlet surface, and this is the surface at the outlet, area at the outlet, area at the inlet, and to the remaining area there is no flow. Correct? Now there are only two areas about which it is flowing. So this, can I write this as over the surface A1, means A inlet. Let us suppose if this is A inlet is the surface, over the surface A inlet, rho times of V bar dot n cap dA plus integral over the surface A outlet. Let us suppose at the outlet section, rho bar V bar times n cap dA is equal to 0. Can I write it like this? Because I have only two areas about which there is the fluid is actually crossing the control volume. Correct? At only two locations the fluid is actually crossing the control volume. Through this, these are thick walls, solid walls, their fluid cannot escape. Okay, so can I write this equation like this? So please type in the chat box, yes or no. So please type in the chat box, can I write these two? can I write this equation? Can I split the total control surface as the two portions where there is inlet and also outlet? These are the two locations where fluid is crossing the control volume. Actually, correct. It is cutting the control surface. Now, at the inlet location, you see this V bar and in are actually opposite to each other. So you can write in and you can write out. For example, if you see, for example, in this case, then at the inlet, this V bar dot n cap is nothing but, dot product of two vectors. If you have A bar dot B bar, this is equal to magnitude of A into magnitude of B into cos theta, if theta is the angle between these two. Okay, if theta is the angle between these two, then A bar dot B bar is given by magnitudes product of both the vectors multiplied with the cos theta. Correct. So now if you substitute here, look what comes out. V bar dot in, both are in opposite directions. So V bar dot n cap, if you see, this is equal to magnitude of the velocity vector, let us say V in into magnitude of n cap into cos theta. Now I told you n cap is the unit normal vector. If this is a unit vector, what is the magnitude of this? 1. Correct. So this, let us write it as V in into cos theta, angle between them. Okay. So now if you replace the integration over the total inlet area density, this is a dot product which is magnitude of V in, which is V in into magnitude of n cap 1. The angle between these two is 180. So cos 180 is minus 1 times dA, plus similarly here area over the outlet into rho V out into dot product. The angle between those two is 0. So cos 0 is 1. So this is dA is equal to 0. The meaning of this is, look, there is a minus sign. Rho is constant. This velocity at the inlet is constant at every section, for example. Okay, then means basically fluid is entering with some average velocity V in. Okay, similarly here fluid is leaving out with some average velocity. Then what you can write at these two sections, you can see rho V in is constant, rho V out is also constant. Means when you take minus rho V in outside, then you have integration of dA, that gives you capital A, total A. Correct. If these two terms are taken out as constants, integration of A dA, integration of differentiation gets eliminated. So this is the total area. So this gives you minus rho A inlet V inlet is equal to, of course we have made one very important assumption that the flow is incompressible. Okay, so that's why we are taking density out. Okay, so this plus rho out rho, if you assume it's constant everywhere, so A out V out is equal to 0 from this equation. So from this equation, what you can identify, if you write two equations on both sides of the equation, rho A1 V1 or rho A in V in is equal to rho A out V out. Correct. This is what you can see actually here, and this is basically told as your continuity equation, which is this continuity equation basically. Okay, so this is how simple terms you will write normally at two sections in the flow. Normally if you don't assume that density is incompressible, then rho in rho out also we write. So rho 1 A1 V1 is equal to rho 2 A to V2. Normally in fluid mechanics in our course we will take this density as constant, so we will write that separately. In thermodynamics and all, you will get this as rho 1 A1 V1 because gases behave as compressible fluids there, so that's why this is the equation. Clear? So if you take any two sections or in a flow, definitely this thing has to be equal if the flow is steady flow. Actually, if the flow is steady flow, then definitely this rho 1 A1 V1 is equal to rho 2 A to V2. Did you understand how did this come? Normally people generally write this expression, but no one tells you how this actually comes, because it comes because of this particular understanding. Clear? Okay guys, I hope it's understandable to all of you. Okay, so if you have any doubt at any point, look, I'm explaining you to simple basics at plus 11 plus 12 level basics. So please, if you have any doubts, please ask me. Okay, I'll be very happy to deal with this. Okay, so anyhow, this is the case. I just thought of showing you this, so we considered this. Okay, next, coming to this applications of linear momentum equations. Okay, so let us write force exerted by jet on a stationary plate. Force exerted by jet on a stationary plate. On a stationary plate. Okay, so force exerted by jet on a stationary plate. Okay, so let us see this. So let us suppose you have a plate like this. You have some plate like this. Okay, so you have some plate like this. And now let us suppose some fluid is going on hitting the plate, for example, something like this. Okay, so it's some simple case I'm taking initially. So let us suppose you have this. Okay, so let us suppose if this is the plate, for example. Now if this is the plate, then take your control volume, because why I'm taking only this as my control volume? Who told me that I should take this? Because of Newton's third law. Look, I'll tell you what's happening. So see here, this is my control volume, for example. If this is my control volume, let us suppose if area of the jet is AJ, for example, and let us suppose if the jet is traveling at a velocity Vj, for example. Okay, area of the jet and velocity of the jet. Okay, this is plate, and let us suppose it is some fluid of density O, normally water jets and all, if you see. So now if you want to calculate force exerted by jet on stationary plate, look, we know from RTT, this is equal to, or from RTT, Reynolds transport theorem, we know one thing. What we know? Net force acting on the fluid. Net force acting on fluid, because fluid is my system, is equal to, this is steady state. Okay, so jet is going hitting and coming down, so things are not changing with time actually. Okay, so in this case, this is equal to integral over the control surface V bar dot, or V bar times of rho V bar dot n cap dA actually. Okay, rho V bar dot n cap dA, and of course relative velocities actually, if you see relative velocities, but here the plate is fixed, so whatever is the fluid jet velocity, same is the VR value. Okay, now in this case it's very important to write one thing here. Look, what is that important thing? Normally, let us suppose if you take this as your x direction and this as your y direction, then it's obvious your force exerted by the fluid on the jet is in x direction, correct? Obviously if fluid go and impact the plate, then force exerted by the fluid on the plate is in x direction, we know that. Okay, let us suppose on y direction there is no friction, nothing, so the jet is just slightly sliding. Jet is smoothly sliding in this case, there is no friction, nothing, so this is coming out at uniform velocity Vj. Okay, so simple as it is. If this is control volume, then jet is sliding smoothly along the plate, there is no friction, nothing. So now if you see, if you want to calculate, for example, the force acting by the jet on the force acted by the jet on the plate, look, you want in the x direction. Okay, so in x direction, this is a vector, so resolve in x direction. In x direction, look, sigma f, net force acting in x direction on plate, is equal to, this is nothing but minus sigma f in the x direction on fluid. Yes or no? Because as per Newton's third law, if fluid is exerting a force sigma f on plate, then plate also exerts on the same force on the fluid. Okay, so this fx on plate is equal to minus sigma fx on fluid. So this is equal to, so this is nothing but the net momentum that is changing. Okay, so the momentum changing in the x direction is nothing but the momentum leaving the control volume in the x direction is nothing but m dot v out in the x direction minus m dot v at the inlet in the x direction, correct? So net momentum which is leaving the control volume is nothing but leaving minus entering, so this gives the net value. Now mass flow rate is just, now we have seen rho av, which is constant. So tell me one thing, whatever mass is coming in, same mass will actually leave, yes or no? Because there is no provision, no tank or something like this to save the mass, so whatever mass is coming in, same mass should leave out actually. Clear? So now that's why, therefore if you see this m dot out, which is m dot, let us say m dot out in this case is equal to m dot in. So let us say this is m dot, for example. Okay, so this is m dot. Now this m dot into fluid at outlet in the x direction. So tell me, this control volume and this control volume, fluid is leaving exactly in the y directions. Is there any fluid which is leaving in the x direction? So please tell me, is there any fluid which is leaving in the x direction at the outlet? Of course leaving. So if you see in this case, is there any fluid which is leaving in the x direction? No, there is no fluid, correct? So therefore this v out x is basically 0. There is no fluid which is leaving in the x direction. So this is m dot times 0 minus m dot times of v inlet in the x direction. Yes, you see, to this control volume the velocity is vj, so vj is what you have. So if you simplify, you know, mass flow rate is equal to rho a v, just now we have seen. So therefore minus rho aj vj into one more vj, so this gives you minus, okay, so I think there is one more minus, correct? This minus should be there because momentum, net force acting on fluid itself is the momentum change. Okay, this minus sign should be there as usual. Only sigma fx is nothing but the momentum change, so minus of this complete quantity, so minus of minus, which is plus actually. So this gives you rho aj vj square. So this is basically the force which is exerted by the fluid on the plate, correct? So because you see fx on plate is equal to minus sigma fx on fluid, so this is equal to minus m dot v out x minus m dot v in x. So this sigma fx of fluid is nothing but this momentum change, correct? So this minus sign which is outside will carry as it is. So rho aj vj square, you see, undoubtedly this is a positive value, which means the force acting on the plate is in positive direction of x, and obviously we know from our understanding, normal from our intuition, that if fluid jet goes and hit the plate, force will be acted on the plate in the x direction. Okay, so that's how this is a positive value, which tells you that the force acted by the fluid on the jet, force acted by the fluid on the plate is actually in the positive x direction. So did you understand how we write this case? If fluid jet goes and hits a stationary plate and get deflected like this, then the net force acted by the fluid on the plate is given by rho a square v, rho a into v square. Now let's go for the calculation of y direction force. For example, if you want to calculate the y direction force, let us say sigma fy, similarly sigma fy on plate is equal to minus sigma fy on fluid, which is equal to the net momentum rate which is leaving and entering. Okay, so m dot v out in the y direction minus m dot v in the y direction. Now tell me one very important thing here actually. At the inlet into this control volume, is there any y component of velocity for the flow? At the inlet of the control volume, is there any y component velocity for the flow? Is there any y component of velocity for the flow actually at the inlet? Type in the chat box. No y, obviously, correct? So therefore at the inlet the fluid doesn't have any y direction velocity at the inlet, correct? So this is 0. So this is equal to minus of, now m dot, look, tell me one thing. When you see, normally if you see, this jet splits into half because it is symmetric. So if you see, half of the jet is moving in this direction, half of the jet is moving in this direction. So if you see, out of the total mass which is entering this control volume, half is going out with a velocity of vj which is pointed upwards, and half is coming downwards with a velocity vj pointed downwards. So since both the velocities are not same, their directions are changing. So therefore you write half of the mass is going at a velocity of vj in the positive direction. So if you see, this is the positive y direction, so this half is going at vj, plus remaining half m dot by 2, the remaining half is going in the direction which is downwards, so this is minus vj actually. So whenever this is minus vj, this answer is 0. So therefore net force acted on the plate by the fluid is 0 in the y direction. Clear? So therefore sigma f y on plate, sigma f y on plate is equal to 0 actually. Clear? So that's how we got the force which is required to the force which is acted on the plates by the jets. Clear? Did you understand how I am writing the velocities, how I am taking the plus signs, minus signs clearly? How I have taken this as minus vj, because we have taken the positive y axis along the upward direction, but this part of the jet which is actually traveling is in the downward direction, so that should not happen. Clear? So here you cannot write plus vj because this minus has to be written because the fluid is actually coming in the downward direction. Okay, now this is one simple case that we have talked about. Now second example, let us see. Force acting on a, force acted by fluid on a stationary curved plate, for example. Stationary curved plate. Fluid on a stationary curved plate. Okay, so let us see this on a stationary curved plate. Now, let us suppose you have a plate like this which is fixed. This is inclined at some angle, for example. So let us suppose we have a plate like this. Okay, so this plate is actually fixed. It is fixed plate. I am telling it is fixed plate, for example. And let us suppose this plate is basically at an angle theta to x-axis. Okay, to the horizontal, for example. Okay, so let us suppose if this is the case, then with horizontal the jet is getting deflected by an angle theta. So let us suppose this angle is basically theta in this case. Okay, so this angle is theta. Now, if you want to choose control volume, then the volume in which the fluid changes its velocity and all is nothing but the volume above this plate. So let us choose the control volume. So let us choose this control volume. The control volume will be generally in the fluid solid contact. Okay, so in this region. So this is the control volume. Okay, so this is my control volume. Now, fluid is actually entering this. Fluid is actually entering this and leaving at this angle. Okay, now you see at the inlet you have this velocity Vj. This is parallel to the x-axis at the inlet, and at the outlet it is leaving at some inclination theta, for example. Okay, so this is entering at velocity Vj, and this is also leaving at velocity Vj. No friction along the plate, so it is smoothly sliding over the plate. Now, if you want to calculate again the force acted by the fluid on the vane, for example, so sigma fx on plate is equal to minus sigma fx on fluid. Correct? So this is equal to minus, now sigma fx on fluid is nothing but momentum change of the fluid. So m dot v out in the x direction minus m dot v in the x direction. Clear? So here if you see this, then we got this v out in the x minus v in the x. So here if you see at the inlet the complete fluid is moving in the exactly x direction. Okay, so let us suppose if you take this as the x direction, positive x, and this is your positive y, for example. Okay, now if you take this positive x and positive y, then what happens? See here, Vj is equal to sigma, this is x and this is y direction. So now if you see v inlet at x, v inlet in x direction is equal to nothing but this Vj, because you see this velocity is parallel to the x axis, so Vj. Similarly, v out at x axis, can you please tell me what is this value at outlet? If this is inclined at an angle theta, so what is the x component of velocity at the outlet? What is the x component of velocity at the outlet? So please type in the chat box. What is the x component of velocity at the outlet? You have your velocity like this. Okay, and this is Vj, I told you, and this angle is theta with the horizontal. So can you tell me what is the x component? Cos theta component, correct? So this is Vj cos theta. And here if you resolve, this is Vj sin theta. Vj sin theta. Okay, so this is Vj cos theta is what you have in the outlet. Okay, so now if you simplify this, this is equal to minus m dot. M dot is same in both inlet and outlet. That's why I have written only single m dot, because it's a steady flow. So now if you see m dot times of m dot can be written as m dot times of v out in the x direction, which is Vj cos theta, Vj cos theta minus this is Vj. This is what you have. Okay, so if you simplify this, m dot can be written as rho Aj Vj If you use this minus, you can shift these two. So rho 𝐴𝐺 square times of 1 minus cos theta is what you have here. Okay, so this is the velocity at which it is leaving. Clear? So rho 𝐴𝐺 square times 1 minus cos theta is what you have basically. Clear? So this is the net force acted on the plate in the x direction. Similarly, if you want on y direction, sigma Fy on plate is equal to, this is sigma minus sigma Fy on fluid as per Newton's third law. So this is equal to minus sigma Fy on fluid is equal to m dot V out in the y direction minus m dot V in the y direction. Okay, so now if you simplify, at this inlet there is no velocity in the y direction, this is 0 because fluid is entering parallel to the base. So this is equal to minus of m dot, which is rho 𝐴𝐺 which we know, rho AV into V out in the y direction. In the outlet we have Vj sin theta, so this gives you Vj square sin theta. So this is the expression for the force acted on the jet, force acted by the jet on the plate. You can see clearly there is a minus sign because obviously it's known to you this force exerted by the fluid on the plate will be in the downward direction, correct? Because you see when the plate is like this, the force will be acting in this direction. So if you resolve, x component will be positive, y component will be negative, which is known to you. So that's why. And also from this equation we find that here we have a minus sign. Clear? This minus sign indicates that the force acted on the plate will be in the downward direction, in y direction. Next, let us go for one more case. For example, okay, see, let us suppose you have this case. For example, let us suppose you have one plate, okay, fixed plate, of course. So let us suppose if you have this fixed plate, okay, so this plate is at some angle, for example, okay, so let us suppose this plate is at some angle. So let us suppose there is a fluid jet which is coming and hitting this plate, okay, there is a fluid jet which is actually coming and moving along this plate, okay, so let us suppose this is the plate, okay. Now if you choose control volume, let us suppose this plate is fixed, okay, this plate is fixed. Now if you take the control volume, for example, so let us suppose you take this control volume, so let us suppose if this is the case, okay. Now let us suppose there is no friction along the plate, then here we have the jet is moving into the control volume with a velocity Vj and it is also leaving with a velocity Vj, velocity of the jet, for example. This is very important for basics of turbo machines, okay. Whenever people teach you hydraulic machines, all these basics are very important, okay, because there you see fluid comes and hit the vane, okay, so all this is fundamental for that. So now if you see this is the case, now let us suppose if this plate is inclined at some angle theta to horizontal. So let us suppose this plate is inclined at some angle theta with horizontal. So let us suppose this angle is theta, for example, with the horizontal. Now my main point here is to identify one thing. Look, let us suppose if the total discharge is Q, then to the upper face you have some discharge which is Q1, let us say, and to the bottom face you have some more discharge which is Q2, correct? Because obviously this plate is not vertical, so jets won't divide symmetrically, there will be certain variation, okay. So whenever jets are at certain variation, then what is the ratio of discharges that this plate will capable of splitting, okay. So let us see that what is the case. So Q1 by Q2, what is the value of this? This is what we want, okay. Now if you want Q1 by Q2, let us see what happens. So this case, now first of all let us try to determine two directions, okay. So first direction is perpendicular to the plate, okay. Let us write this Q1 by Q2 somewhere here. What is the value of Q1 by Q2, okay. Let us write here also Q1 by Q2 is how much? This is what we want, okay. So what is the ratio of this plate? And this plate is inclined at some angle theta to horizontal. So now try to see this. if this is q1 by q2, let us define two directions in the positive sense. So let us suppose if this is the direction normal to the plate, and let us suppose this is the direction which is parallel to the plate, for example. Okay, so this is the direction parallel to the plate and this is normal to the plate. Okay, so let us write, or else you can write n and t, normal and tangential components, for example. Okay, so you see some component is normal to this and some is tangential to this, okay, which is basically smoothly sliding along this. Okay, now first of all, if you want to calculate q1 by q2 value, you know, from continuity, you know, this is steady state actually. So from continuity, net mass crossing the control volume should be 0, means whatever is entering that should come out. So q is equal to q1 plus q2, correct? This is one equation from the conservation. Yes, so q is equal to q1 plus q2. Okay, so the total mass q or total discharge q is basically split into two parts, which is q1 and of course q2. Now try to understand this. If I ask you one thing, look, this fluid is coming like this and it's smoothly gliding. Okay, so this fluid is just smoothly sliding on the plate. Whenever the fluid is smoothly sliding on the plate, we have seen already what is the component of velocity in the tangential direction. So if you see, this is basically net force acted by the fluid on plate in tangential direction, in tangential direction is 0, correct? This is basically 0, right? Because you see there is no tangential you know, impact that's happening. Whatever is coming, it's just changing its momentum, that's it. Okay, so now let us see, this implies sigma f in the tangential direction on plate is equal to minus of sigma f t on fluid, which is equal to minus of m dot v out in the tangential direction minus m dot v in the tangential direction. So this quantity is equal to 0, correct? Because if you see, there is no tangential force that's actually acting on this location. Okay, so therefore if you see, then you have this minus sign can be cancelled, no issue, no impact of this minus now. So this implies at the outlet, if you see at the outlet, fluid is actually having two velocities, I mean the same velocity, but of course in the different directions. So you see q1 amount of discharge is going at positive velocity because t is taken in the upward direction. q2 amount of discharge is traveling in the negative velocity. So here if you see at outlet, rho times of q1 into this velocity is in the positive direction, so vj, plus at the outlet some other part is traveling at minus vj, so rho q2 times minus vj is what you have. Okay, so rho q2 times minus vj is what you have, minus at inlet. So inlet, everything is coming at uniform velocity. So here if you see, your velocity is horizontal in this direction, vj. So if you resolve this into components, for example now tangential component and this component basically here. Okay, so now these two are normal components and here this angle is theta with horizontal. So this is vj cos theta is the tangential and vj sin theta is normal component. Okay, so in the tangential direction, you see this is along the positive arc, correct? If this is v, then the resolution will be like this. So therefore here this is the direction of vj cos theta, so minus rho q, because the total discharge is having the same velocity here at this inlet, so v cos theta is the direction in the tangential component. So vj times cos theta is equal to 0, correct? So this is what you have. So this total expression is equal to 0. Is this equation clear? Did you understand how I have written this? Because at the outlet, fluid is spread into two parts, for which that the direction of the velocity is different. So that's why I have written the outlet component as two parts, two separate parts. Okay, now if you see, if you simplify this, density is common in every term. So if you cancel this, then what you have else, vj is also common in every term. If you cancel this vj also in every term, then what is left with you? Clear? So now if you see, this implies q1 minus q2 is equal to q cos theta. This is the second equation that we have obtained. So q1 minus q2 is equal to q times of cos theta. So this is the first equation and this is your second equation from this. Okay, so this is first equation. So from these two equations, explain third term, this term. So see here, your point of interest is you are writing in the tangential direction, correct? But here the velocity is in the horizontal direction. Okay, so whenever you are writing force in the tangential direction, this is v. So this is the tangential component and this is the normal component. Okay, so the angle made by this tangential direction with horizontal is theta. So if you want a tangential component, this angle will be theta. Since this is Vj, this will be Vj cos theta and this will be Vj sin theta. So that's why I have written the inlet velocity as Vj cos theta. So this is why we have taken this value as Vj cos theta. Okay, got it? Now rho Vj is constant in every term, so we have eliminated. So q1 plus q2 is equal to q. Therefore q1 plus q2 is equal to the total discharge, and q1 minus q2, if you see, this is equal to q1 minus q2 is equal to q times of cos theta. So now if you simplify these equations on adding, if you add them, for example, you can add them directly. So if you add, because you want q1 by q2 value, okay, so if you add them, let us see what happens. If you just add them, q2 minus q2 gets cancelled. So 2q1 is equal to q plus q cos theta. So q, if you take common, 1 plus cos theta. So q1 value is equal to q by 2 times of 1 plus cos theta is what you have. Okay, so now if you substitute q1, I mean q1 is equal to q by 2 times of 1 plus cos theta in any one of these equations. Let us substitute in the first equation. So 1 implies q2 is equal to q minus q1. So what is q1? Q by 2 times of 1 plus cos theta. So if you simplify this, we get q, if you take out 1 minus 1 plus cos theta by 2 is what you have. So if you take LCM, this 2 minus 1 minus cos theta by 2 is what you will have. Okay, so q by 2 times of 1 minus cos theta is what you have for the q2, just if you substitute. Okay, so this is the q2, which is the bottom part of the flow. So therefore from these two equations, q1 by q2 is equal to q by 2 times of 1 plus cos theta, and this guy here is q by 2 times of 1 minus cos theta. Okay, so now if you see, if you cancel this q by 2 and q by 2, then this, of course these are the individual discharges. So anyhow, if you just want the ratio, q1 by q2 is equal to 1 plus cos theta by 1 minus cos theta. So this is the ratio of these two discharges in which they split actually. Clear? So q1 by q2 is 1 plus cos theta by 1 minus cos theta. Clear? So this is how we have the things, of course. Okay, so look, I'll tell you one thing. Let us suppose if theta is 90, for example. Okay, so let us suppose if theta is 90, means the plate became vertical. Okay, so when plate becomes vertical, we have seen that when plate is vertical, jet splits into two equal halves, correct? So which can also be understood from this equation. If you put theta equal to 90, cos 90 is 0, so these two cos thetas will go to 0, so 1 by 1, which is 1. Okay, so q1 and q2 will be equal. If you want, you can write that if theta equal to 90 degrees, q1 by q2 is 1 actually. Okay, which you generally know. Okay, so this is how the two discharges are actually split if the angle is 1 plus cos theta and 1 minus cos theta. Clear? Okay, now let us see jet impinged on a cart, for example. Jet impinged on a cart. Jet impinged on a cart. So let us suppose you have an inclined plane, for example, which is making some angle theta with x-axis. On this inclined plane, let us suppose you have some cart, for example. Okay, so some cart is also there. So let us suppose there is some cart like this. Okay, so fine. So there is some cart. Okay, now to this cart, let us suppose there is a vane which is attached, for example. Okay, so to this cart there is a vane which is attached. There is some vane. So there is some vane which is attached. Okay, so now whenever there is some vane attached, look, obviously when you try to hit a jet, let us suppose there is no friction, just smooth surface. So this has a mass m, for example. This has a mass m. Okay, so whenever this has a mass m, let us suppose this has a vane in this particular direction. So you are impinging some fluid onto this. So some fluid is going in and coming out like this. Okay, so it's that it is putting some force on the cart. Okay, now let us suppose if jet area is aj and the fluid is having some density O, what should be the velocity Vj such that the cart won't come down? Okay, so basically what happens, if you see, if you leave the cart, there is some mg sin theta that pulls the cart downwards. So this, because of that mg sin theta component, the cart will actually start moving down. But by the time you apply some force like this, then what happens here, when you apply this force, then definitely this cart will be at that particular position, correct? So let us try to calculate what is the Vj value, minimum velocity of the jet, so that this cart will remain stationary there. Okay, so let us see that. So first of all, if you draw the free body diagram of the cart, for example, if you draw the free body diagram of the cart, then you have the weight of the cart, which is mg. If you resolve this along the plane and perpendicular to the plane, of course no friction anyhow. So if you resolve this, so if you see, look, this angle is theta. This is the angle between plane and horizontal. So if you take the angle between normal to the plane and vertical, this angle will also be theta, correct? Because angle between two lines is same as angle between the normals, correct? So therefore, if you see, if this is the case, then if the angle between the plane and the horizontal is theta, then angle between the vertical to the plane and also this vertical is, means angle between normal to the plane and vertical will also be theta. So obviously this is mg sin theta and this is mg cos theta. Mg cos theta, correct? So now what happens when you apply this jet is, the jet actually applies some force in this direction. So this is force applied by the jet in the tangential direction. So obviously when you hit a jet like this, jet will, since the jet is coming out at some angle, definitely there is some tangential force which is applied on the this mass on this mass by the jet actually. Okay, so now if the block should not fall, then definitely at equilibrium what should happen? At equilibrium, you know what should happen here? At equilibrium case, definitely whatever is the mg sin theta, that is, sorry, I think I have written reversely here. This is cos theta and this is sin theta, because this is the angle, this is the component which is touching the angle. No? So here we have mg cos theta and mg sin theta. Okay, because if you see, this is the line which is touching the angle. Always the line which touches is cos and this is sin. So at equilibrium, mg sin theta is equal to f on sigma f, or you can write sigma f, or only one force is there, so let us write directly ft on mass by fluid, correct? Force acting in the tangential direction. So let us suppose tangential, if you take in the positive direction like this, so this equation implies mg sin theta is equal to minus Ft on fluid by mass. Correct? So this is equal to minus of, now net force acting on the fluid. So how Fz in upward direction we will see now. Okay, look, I am trying to calculate in this particular direction. If I get a positive value, then definitely force is on the Fz direction. Okay, obviously what happens whenever jet is applied, it tries to push the block actually, correct? So it tries to push the block actually like this, so that the movement of the block is tending to be in this direction. Okay, so whenever this jet is coming down, look, whenever jet is coming down, the normal reaction, look, jet is coming down in this direction now, so normal reaction will try to be in the opposite direction. Okay, so that's how force on the block, means basically force on the vane is in the upward direction. Okay, so let us see, minus m dot out v out in the tangential direction minus m dot in v in the tangential direction. Okay, so let us simplify what is the case. So minus of m dot is same, because whatever the fluid that entering, because means normally if you take this as the control volume, then whatever fluid is entering, same amount of fluid is actually coming out. Okay, so now if you substitute there, m dot times of, at the outlet velocity is Vj, because there is no friction along this plane, so smoothly it is sliding. But since t is in the opposite direction, Vj is in this direction, so we will go for minus Vj actually. Okay, why we have written minus? Because this t tangential direction we have taken in the upward direction, but the fluid jet is actually coming down in the bottom direction, so that's why we have taken a minus. Okay, so minus m dot times of, at the inlet, tangential velocity at the inlet. Look, again same thing, velocity is in this direction at the inlet, so this is the angle theta and this is t, so obviously Vj cos theta is there in that direction. Okay, so Vj cos theta, it's in the positive direction, correct? Vj cos theta is there actually, correct? Yes or no? Because velocity is coming in this direction, so at this, in this inlet, the tangential component of the velocity, if you resolve to tangential and normal velocities, then definitely this tangential component is Vj cos theta and this normal component is Vj sin theta, correct? So that's how, if you see, minus m dot Vj cos theta. Now you see all over the minus, if you see this total value, force acted in the tangential direction on the mass is a positive value, correct? So what is m dot? M dot is equal to rho aj Vj into, there is one more Vj in both the expressions, so Vj square times of 1 plus cos theta. So this is what you have basically. Okay, so therefore here this equation of equilibrium is mg sin theta is equal to rho aj Vj square times of 1 plus cos theta. That's it. Okay, so this is the simple equation. So if theta value, mass, all are given to you, you can easily calculate what is the velocity. Means out of all these things, theta will be generally given, they will give the angle. So out of the remaining quantities, if they miss one of the quantity, you can find it using this equation. Okay, look, don't try to remember these equations, okay, because that won't help you in exam. You should know how to write these equations, right? To how to write these components, understood? So this is a positive value, as I told you, because you see, whenever the fluid is trying to move in this direction, the reaction force will try to move this plate, move this vane in the upward direction. Okay, so that's why the force acting on the vane is actually in the positive direction of t. So let us continue. So basically these are the cases, whatever the inclinations they give you, plate, whatever they tell you, the main story is to write this velocity components little carefully. Okay, if you can write them carefully, that's it, things are fine. Clear? So this is the governing equation in this case. This is how we get this. Okay, so this implies, if you want, you can continue this term all over to all the steps. Mg sin theta is equal to mg sin theta is equal to mg sin theta is equal to that. Okay, how v square, mass flow rate, there is one velocity. Okay, m dot is rho aj vj, correct? There is one more vj in the velocity components now, so we have taken that velocity also out. That's it. Clear? M dot is rho aj vj. Here I didn't write vj's, okay, because you see this vj I have already taken and written square here. So that square is basically from the velocity terms. That's it. So now let us see the moving vanes now. Okay, so we have seen the stationary cases, whatever could be the case. This is how we act. Now force exerted on a moving vane. Five. Force acted by the jet on a moving vane. force acted by the jet on a moving vane actually. Okay, so let us see. Now let us suppose you have this vane, for example. Okay, so you have this vane or plate generally. So let us suppose if there is some plate, but this time this plate is not silent, this plate is moving with some velocity. So let us suppose if this plate is moving with velocity v plate, for example. Okay, so v p, for example, vp stands for p stands for plate. Okay, so it's moving at some velocity. Now obviously what happens? So there is some fluid which is coming and impacting with the plate actually. Fine. So let us suppose if this is the case. Okay, so jet is coming in with a velocity of vj, for example. Jet is also moving with some velocity which is vj. Okay, and let us suppose you have some area of cross section for the jet aj as usual. So this is aj. Okay, so this is basically the jet which is moving. Now try to understand something. If you want to calculate what is the force, because the plate is actually moving in the x direction, so let us suppose if you take this x and y directions, x and y, normal these directions. Okay, so x direction and also this y direction, for example, in this case. Now if that's x and this is the y direction, then try to understand this. This plate is actually moving. Now if you take the control volume, now in this case, if you take this control volume, for example, so if you take this control volume in this case, okay, now if you see this fluid is also moving here, this is moving at vj. Okay, so this is also coming out at some velocity basically. So what is the outcome velocity? We have to identify. Okay, so now if you see, whenever the, first of all try to understand one thing, here the plate is not fixed, so the plate has certain velocity vp, so jet is also traveling. Now tell me one thing, if you take the mass which is entering the control volume, okay, so m dot, for example, can I write rho ap, sorry, a jet into v jet? Can I write this expression? Can I write this expression this time or not? Look here, whenever the plate is fixed, you know this is the expression, but whenever the plate is actually moving, the mass which is coming in at one particular point, the total mass cannot enter the control volume. Yes or no? Because the control volume is also moving with some speed now. Yes or no? So the control volume is also moving. So whenever the control volume is also moving, if the fluid is trying to enter the control volume at velocity vj, then definitely since control volume is also moving, the complete fluid which is coming cannot enter the control volume. Yes or no? There is some difference. Can you understand this? Correct? Yes or no? Are you all getting? Basically what I am telling you is, if you see in this case, whenever the fluid is coming and trying to enter the control volume, this control volume is also moving with some speed. Then how come this total mass fluid is actually entering the control volume? It cannot enter, correct? So therefore rho aj into vj minus velocity of the plate. So this is the mass fluid which is actually entering the control volume. Okay, because there in the derivation we have assumed that the control volume is fixed. There, except there everywhere I have written the velocity should be relative velocity, correct? So whenever you are writing relative velocity, I have written that term rho v r bar dot n cap dA, if you remember. Okay, so if this is the mass fluid, this velocity has to be the relative velocity, definitely. Clear? So that relative velocity has to be made. Okay, if they give m dot directly, if they give you mass fluid and all, it's okay, but if mass fluid nothing is given, you have to use this expression. Okay, if they give you this much amount of mass is entering control volume, you use m dot directly, but here if you see we have vj minus vp. Okay, because relative velocity has to be substituted here. Clear? So that's the case. Now m dot is equal to this. Now So what is the velocity at which this is coming? The relative velocity at this point is, which is coming in, is Vj minus Vp. Similarly here, so if this is entering at the relative velocity Vj minus Vp, then it leaves, whenever there is no friction along the length of this plate, you have Vj minus Vp. Similarly here, Vj minus Vp is the relative velocity with which the fluid actually comes out, okay, because it's the relative velocity. Clear? So let us apply that equations here. Now sigma fx on plate, sigma fx on plate is equal to minus sigma fx on fluid. So this is equal to minus m dot out V out in the x direction minus m dot out in V in the x direction. So whatever the mass is entering, same mass should go out because it's steady state. So therefore, if you see, minus m dot times of V out in the x direction. At the outlet, there is no velocity which goes in the x direction. So therefore, this quantity is actually 0. Minus m dot in, which is m dot times of inlet velocity in the x direction. So the velocity with which it is entering the control volume is Vj minus Vp. Vj minus Vp. Okay. So minus of this minus gives you plus sign, and m dot is rho Aj times Vj minus Vp. So this is totally equal to rho Aj into Vj minus Vp square actually. Okay. So this is sigma f on plate by fluid, of course. Okay. So only the fluid is exerting the force on this F. So you can see this is the case. Okay. Now this is what we have here. Okay. So P rho Aj times into Vj minus Vp whole square. Now let us try to understand one more thing in this case. Okay. So this is the case. Here I want to angular momentum equation came now already. Just a minute. Let us send this to some deep. We have few more things to discuss. So see here. Okay, fine. So now let us suppose, because of the impact of the jet, the plate is moving. Okay, so the movement of the plate is due to the impact of the jet. Okay, now means one thing I can tell you, because of the impact of the jet, if plate is moving, the force applied by the jet on the plate is responsible for the motion of the plate, correct? So in such cases, the fluid is actually doing some work because it is pushing the plate, correct? So there is something called power. So power delivered by the jet, power delivered by the jet is equal to F on, of course the motion is only in the x direction, so F on plate. Okay, so force on the plate in x direction multiplied with velocity of the plate in x direction, which is nothing but Vp already. Okay, so now if you simplify this, this expression gives you rho A jet into V jet minus Vp whole square into Vp. So this is the power delivered by the jet. Power delivered on plate. Power delivered on plate. So now if you want to see one more thing, you know, force, power is equal to force into velocity. So we have seen this expression. Now definitely, look, let us try to understand. If you use Vj, it means normally velocity of the jet can be changed. It can be in your hands. Normally in case of turbines and all, what happen? There is some throttling and governing mechanism for controlling the flow rate actually. Okay, you can reduce the cross section area in case there are certain things. So therefore, if you see, for power delivered to be maximum, what could be the relation between velocity of the jet and velocity of the plate? Let us try to observe here. Okay, so for the power delivered by the jet to be maximum, the power delivered by the jet, the power delivered by the jet to be maximum, power delivered by the jet to be maximum, you know, Let us suppose if you are restricting this velocity of the plate movement, for example, let us see. So let us suppose if this fluid jet is maintained constantly, but this plate motion is actually restricted. Okay, you can change this because you can change the locations of the impact of the jet so that the velocity can change. So if you see dp by du plate or v plate generally, if you see, is equal to 0 because jet has fixed properties. Let us suppose if jet is coming at uniform velocity, if jet has certain area, fluid is at density, then what should be the velocity of the plate, or what should be the relation between plate velocity and the jet velocity so that the power delivered is actually maximum. So let us try to understand that. So this is equal to d by d vp of rho aj vj minus vp whole square into velocity of the plate is equal to 0. So now in this there are two constants, this density and area of the jet, these are constants, they have nothing to do with this. So this implies differentiation of this. Okay, so first function into derivative of second function. So if you see vp is basically there is no there is nothing like so differentiation of vp with respect to vp is 1 plus second function into derivative of the first function. So what is the differentiation of first function? 2 times of vj minus vp into its inner differentiation. So what is the inner differentiation value? Differentiation of vj is 0 because jet velocity is a constant velocity. V plate differentiation is with respect to v plate, so this is minus 1 is equal to 0. Okay, so just I am differentiating the things. Now if I differentiate, I can cancel some terms. This vj minus vp and this square can be cancelled. Okay, so if you cancel this, we have vj minus vp plus 2 vp into minus 1, so total minus 2 times of velocity of the plate. This is equal to 0. So this gives you velocity of the jet is equal to 3 times of velocity of the plate. So therefore velocity of the plate is equal to velocity of the jet divided by 3. Okay, so this has to be the relation for the power to be maximum actually. Clear? Okay, so the power should be maximum in this case. Okay, so if you replace this vp as v jet by 3, you can get p max. Okay, so therefore p max is equal to p max is equal to here rho aj into vj is vj constant, vj minus velocity of the plate is vj by 3 whole square into vj by 3. This is velocity of the plate. So if you see rho aj, this square gives you 4 by 27 actually. Okay, so if you see this, if you simplify this 2 vj by 3, so square of that 4 vj by 9 and into vj by 3, so total 4 vj cube by 27 actually. Okay, so this is what you have, 4 by 27 times of density of this aj into vj cube is what you get actually in this case. Okay, so this is the maximum power that can be delivered by the jet onto the plate actually when plate is actually moving in this case. Clear? So anyhow, but normally that need not be remembered, but this condition if you keep in mind, it will be somewhat helpful to you in some places. Okay, fundamental mechanics that I'm doing. Power is equal to force into velocity. Then if you want maximum power, you have to differentiate that and equate to 0, all these things. Okay, fine. So all these things are the basic fundamental things. Okay, so that you have, that you generally see outside also. So let us see one more case. Force exerted by the jet on a curved moving vane. Okay, so here also the vane is basically the vane is curved, but it's actually moving. Okay, so let us see. Force exerted by the jet on a sixth case, let us say, what any number of cases, I don't bother. So see, force exerted by the jet on a moving curved vane, actually. Okay, so once you know that linear momentum equation, all these things are simple. Okay, just writing the velocity components little carefully can give you the correct answers. So now everything is same, only thing is this vane is moving. Okay, Okay, now this is x direction and y direction. This is y direction. Okay, so x and y directions is what you have. Now in this, fluid is moving. Okay, so if you see this x and y, now let us see, this plate is actually moving with some velocity, u plate. Okay, so let us suppose this plate is moving with some velocity v plate, for example. Okay, plate is not stationary, plate is also moving, sometimes it can move when fluid hits. So let us suppose if the fluid is trying to come with a velocity vj, for example. Okay, velocity of the jet is the velocity which the jet is trying to move, enter. Okay, so definitely you can see the relative velocity at which this enters is vj minus vp. So let us suppose whenever there is no friction along the this vane, then this velocity is also vj minus vp. Vj minus vp, correct? Because you see along the plate there is no friction, we are assuming. Normally sometimes in hydraulic turbines what they give you, they'll give you the ratio of relative velocity. Okay, you might have seen one constant in your books, k is equal to relative velocity at the outlet by relative velocity at the inlet. They'll give you normally around some 0.85 to 0.9, such range. Okay, they'll give you somewhere around these values. Normally you might have seen this there, because actually the blades, after certain usage, what happens, because of the high velocity impingement of the liquid, what happens is the blades get eroded smallly. Okay, so because of that, over a period, what happens on the top of the blades, there is something called pitting, you might know, which is called the surface failure. Okay, have you heard this word pitting? Normally pitting, normally even when we were working in HPCL, few times what happens, these pipes, normally they have some non-corrosive pipes, nace pipes actually, but normally sometimes because of very high usage, sometimes there is some rusting, means surface failure actually. Okay, so I'll show you some pitting if there is possibility, because that's a good thing to see as a mechanical engineer. I'll show you. So see, because normally pitting is the surface failure that you see, so this kind of failures. Okay, so pitting is one type of corrosion, of course. So let me open the images so you can see. So these failures, okay, you can see this is very severely pitted actually. Okay, so this pitting is actually very severe in this case, but but normally in industries we don't allow this much level. Okay, we, as soon as the impact starts, we will immediately start taking some remedies of that. Okay, so let us see if it gets loaded. I will show you. So all these are basically pitting. You see this surface failure. Okay, so this kind of failure is called the pitting. It's basically some type of corrosion. Okay, so on blades what happen, whenever this fluid flows with very high velocities and all, so sometimes this they actually erode the surfaces. Okay, so that's why this pitting happens, the surface failure happens. So the fluid cannot smoothly slide, the efficiencies of the machines will fall definitely. Okay, because outlet velocities will decrease. Okay, so whenever the outlet velocities are decreasing, then definitely momentum change will decrease. So force acting on the by the fluids on the rotors or on the blades, on wherever, it will actually decrease. Okay, so whenever it is decreasing, your immediate job is to maintain that. Okay, to handle the equipment. So in such cases, normally they'll give you the velocity coefficients here. Okay, so k is equal to vr2 by vr1, which is 0.85 to 0.9 on an average. This will be the case. Even this is 0.85 to 0.9 is also very large. Okay, normally in some power plants and all, whenever that value comes below 0.9, normally if you see, immediately within minutes they'll start maintenance work. Okay, because even normal in case of hydraulic turbines and all, what happens, even if there is let us suppose if a plant is producing some 2 megawatt power, for example. Okay, means for 1 second the output from the plant is actually 2 megajoules. Okay, so it's a very tremendous energy. So out of that 10% is lost, means basically what happens, out of 2 million joules, 2 megajoules, 10% you are almost losing. So 20,000 almost you are losing. Okay, so 20,000 is almost still a big value. So that's why they immediately go for maintenance in some cases. Okay, when we were working with HPCL also, we have seen some pitting failures which cause severe damage, especially to pumps. Okay, so this is very dangerous. Now see here, guys, I'm not telling you separately that this is interview question, this is that question and all. Okay, whatever I'm telling you, almost I might have covered some roughly some 40 to 45 interview questions till now. right from fluid and its properties to till this moment. Okay, so if you understand the subject easily, then definitely you can answer all the interviews. I myself have cleared the toughest BRC, so you will also be able to clear that. Okay, if you follow at least for these subjects what I am teaching you. If you see this is Vj minus Vp. So obviously if this is entering, this is smooth surface. For example, let us suppose if there is no loss of any fluid energy, then definitely it goes out with Vj minus Vp velocity. So let us suppose the inclination this makes with the horizontal is theta, for example. This inclination what we make is theta. This is theta. Okay, so this is theta, this inclination is theta. Now if this inclination is theta, then let us see here sigma fx. If you see in the x direction, the forces, if you take so these are the x and y direction forces. Okay, so x and y direction forces basically here. So now if you see fx, sigma f on plate, sigma f in the x direction, let us write in the x direction, sigma fx on plate is equal to minus sigma fx on fluid. So this is equal to minus, okay, so this is equal to minus. So if you see this case, minus, look here there are no other pressures than the atmospheric pressure. Okay, so a complete thing is happening in the atmosphere, so there are no excess pressures. But sometimes in case of pipe flows and all, I'll show you later, what happens is basically in case of pipe flows and all, this pressure means, let us suppose if there is a pipe, then at this section there will be some pressure due to the beside fluid, and at this section there will be some different pressure, okay, because of the pressure loss along the pipe. Okay, so we will see certain things also in today's session. Okay, so now if you see minus m dot out v out in the x direction minus m dot in v in the x direction. Okay, now if you simplify this, let us see what happens. This is equal to minus, so whatever mass is going in, same should come out, m dot times of v out in the x direction. So what is velocity at the outlet in the x direction? Vj minus Vp is in some inclination. So if this is Vj minus Vp, so this is inclined at some angle theta, for example. Okay, so if this is inclined at some angle theta, then this is Vj minus Vp cos theta. Okay, so this is Vj minus Vp cos theta. So therefore Vj minus Vp cos theta. Okay, so Vj minus Vp cos theta minus m dot in times of, so minus m dot in times of Vj at the inlet, in the x direction, this is Vj minus Vp straight away. Okay, so this is the total mass flow which is actually happening. So m dot in and m dot both are same actually, so this can be written as m dot actually. Now if you see, if you delete this minus sign, you have m dot times of Vj minus Vp times of 1 minus cos theta, correct? So this is what you have, because some part of the momentum is actually decreasing at the outlet direction. Okay, so this is 1 minus cos theta. So m dot is, again you see, whenever the fluid is trying to enter the control volume, this plate is actually moving, so definitely net effective m dot that happens is, if you write relative velocity, rho aj Vj minus Vp whole square. Okay, Vj minus Vp, that's it. Okay, so that's the basically that's the mass flow which is entering the control volume. So rho aj times Vj minus Vp times of 1 minus cos theta square, because you see this rho aj Vj minus Vp and one more Vj minus Vp is there, so that's why this Fx, force acted on the x direction on plate, is equal to this value. Okay, so this is what you have basically. So this is the force acted on the plate in the x direction actually. Clear? Okay, simple expression. Again, the main art here should lie in writing the velocity components. Okay, and of course mass flow rates is based on the relative velocity, so you know this. So these things has to be written little carefully. If you write those things, then things are very simple. Okay, clear? So AJ. Now, similarly, if you want Vy in the y direction, you can calculate this inlet in the y direction is 0. This will be V out will be Vj minus Vp sin theta. Okay, that's it. Okay, if you do, then you will get the answer in the negative sign, because obviously this jet will try to exert a force in the downward direction, in the vertical direction. So we have this. Okay, now let us see. So we can do a lot of things like this. If you keep on talking, we can frame different number of examples. Actually, you can create different geometries and all, and you can do. Okay, like for example, you see, I'll give you one more last case. For example, look, let us suppose there is a cart, for example. Okay, let us suppose there is a cart. This cart has some wheels, obviously. And let us suppose we have the road like this somewhere. Fine. So this is road, for example. Okay, so there is some road like this. Okay, so there is one more wheel also. The cart cannot just stand on one wheel. Let us keep one more wheel, for example, like this. Okay, so now these are the two wheels of the cart. Now let us suppose on this cart there is one big tank. Okay, so let us construct one tank also. Let us suppose it is inclined actually. Okay, so it is inclined. So let us suppose there is some edge like this. Okay, it's not closed basically. Okay, this is closed, of course. So if you see, this has some angle which is made like this. Okay, so there is some angle which it makes. This angle is theta. So here if you see, this angle is theta. This angle is theta. Now see here, what happens? Let us suppose if it's a large tank, for example. So it's a large tank. So let us suppose there is some fluid like this. So let us suppose the tank has a small opening, because of which the fluid is actually coming in this direction. Okay, so the fluid is actually coming in this direction. So the fluid is actually coming in this particular direction. Okay, so let me draw a little neatly. Okay, so there is some fluid which is coming in this particular direction. Okay, it is being thrown out at some velocity like this. Okay, so this is V. Now I want to ask you one thing. Try to answer this. Whenever the jet is trying to move in this direction, whenever the jet is actually trying to move in this direction, please tell me what will be the direction that the cart will try to move. Actually, means when the jet is actually moving in this particular direction, what will be the direction? Right side or left side will the cart try to move because of the reaction force? So please tell me. Jet is actually moving in that direction. Okay, so opposite to jet, correct? So basically, if you see, whenever the fluid is actually whenever the fluid is moving in this particular direction, then the jet actually means basically then the this cart will actually try to move in the left direction, correct? So whenever the cart is trying to move in this direction, then to stop that, what we have done is we tied a string onto some support which is there, for example. Okay, so let us suppose there is some support, to that we have tied a string. Okay, so this is a fixed support again. So this is a fixed support. So whenever this is the case, then definitely look, these are all some examples basically. Yeah, it tries to move the left side obviously. So now if you see, my main intention here is to calculate whenever this card tries to move in this direction, definitely this cable which is tied here will get tightened, correct? So there is some tension in the string, yes or no? Because of this, there is fluid which is coming and leaving out in this direction. So in such case, what happens basically, the cable which is connecting the cart with the support will actually be in some tension, correct? So if you see, this is in some tension, this will be in some tension actually. Okay, so let us see what is the value of the tension in the cable. Tension in the cable, T. So what is the value of this? We have to identify that. Okay, so let us see here. Now if you see, you want to choose a control volume, correct? Because if you see, you should know the net force acting on this cart. So obviously if this system has to be stationary, this is T should be equal to net force acting on the cart, correct? But T is in the opposite direction, so this is in the other direction. Okay, so if you see, T is equal to minus sigma F on cart, correct? Obviously, because this, if you see, tension will try to, when the force on this cart is in the leftward, this tension will try to pull this rightward, so that because of equilibrium they are in static condition. Okay, so when they are in static condition, look what happens. They are in static condition, of course. So when they are in static condition, let us see what happens out. Okay, okay, this is on cart. So now if you see, this is x direction and this is y direction. So obviously this sigma F on cart is equal to minus sigma F on cart is nothing but minus sigma F on fluid. Sigma F on fluid actually. Okay, so this implies, you can see totally, this implies tension in the cable is equal to minus of minus is generally plus, so sigma F on fluid. So what is sigma F on fluid? You see, for example, let us suppose the opening is of some area. So let us suppose if AJ is the jet area, for example, if this is coming out with a velocity Vj, for example, cart is stationary, of course cart is not moving, then in that case, if you see, the momentum change on the fluid which is equal to m dot out V out in the x direction minus m dot in V in is what you have, correct? So let us suppose, let us write in the next line, so that could be better. Tension in the cart is, and the cable is equal to m dot out V out in the x direction minus m dot in V in the x direction. Okay, so now if you see this, if you see this case, m dot out V out x minus m dot in V in x. Now tell me, look, your point is to calculate the tension in the cable. So let us suppose if you select the control volume in this way, there is no friction at the wheels and all. So tell me, in this case, if you see, there is only fluid which is leaving out and the cable is out of this control volume. So can you please tell me what is the value of this V inlet in the x direction? If this is the control volume choice we have taken, because you see practically at the inlet there is no velocity. Okay, this jet is connected to the cart. So if you take the control volume such that the complete cart is actually in the volume, so can you feel, is there any inlet velocity in the x direction into the control volume? This is 0. Okay, there is no inlet velocity into the control volume, but out of the control volume, yes, this fluid will actually go out of the control volume. So whenever the fluid is going out of the control volume, m dot out, m dot into V, which is practically present. So m dot is rho times of this A jet into V jet velocity. So AJ into Vj square, and of course outlet velocity is Vj cos theta actually, because you see this is V, it is at some angle. So definitely whenever this is at some angle, theta, then this is V cos theta. Okay, so this is V cos theta. So obviously this is Vj square cos theta. So that's how the tension in the cable is. Obviously, you see this is a positive value, so obviously tension will be within this control volume. You know, the tension is actually in the right side. So how I are taking the control volume, sir? Because look, I cannot take only this part as the control volume, because this cable is actually connected to the cut. Okay, so if I want to talk about something about the cable, I have to take cross section in such a way that it should actually pass through the cable. Okay, so and also this tank is actually mounted on this cart actually. Okay, so whenever the tank is mounted on the cart, then this tension is directly related to this fluid, so I cannot take this particular value as the control volume. Okay, because that just gives me the force acting on this vane in the direction. Okay, if I want the force acting on the cart, I have to take the complete volume. Correct? If I take only this part, it just gives me the force acting on the vane, that's it. But that should not happen, right? We want the force acting on the cart actually. So definitely cart should come in the control volume. Clear? So that's why we have taken this. Okay, so rho aj Vj square cos theta is the value in this case. Okay, so therefore this tension in the cable is equal to rho aj Vj square cos theta is the tension that actually lies in the cable. Okay, so this is rho aj Vj square cos theta. Clear? So that's how we have the things. Okay, so basically this cut in this case. So like this, if you keep on framing, you can large number of questions actually. Okay, similarly in this case, like you know, whenever there is a 5 hose, 5 fighters and all. One last case I will tell you before going to angular momentum equation. So see here, normally force required by firefighters to hold the nozzle, force required by firefighters to hold the nozzle. To hold the nozzle. Okay, so for what happens sometimes? Okay, so if you see there is some nozzle, okay, so let us suppose if this is the nozzle, for example, from which the fluid is actually coming out. Okay, from which the fluid is actually coming out in this case. Okay, so the fluid is actually coming out with some velocity v. Okay, whenever the fluid is coming out with some velocity v. Now on this side you have hoses. This is a hose. Okay, so hose, normally you see the hose what the firefighters will hold, and the nozzle will actually direct the fluid to some particular location. Okay, water. So this is actually some hose. So this hose is generally connected to some large tank, correct? So whenever this hose is generally connected to some large tank, this inlet will be small in this case. Okay, so slowly the fluid picks up energy and it actually throws it with some velocity v. So in this case also the force needed by the firefighters F is equal to rho aj into v square. Okay, same thing, because velocity out minus inlet velocity we neglect, because you see inlet is at some far location, so that's why there is no impact on this region because of the inlet fluid at some far location. Okay, so that's why in this case also we take rho aj into v square. Okay, if you want vj you can keep vj here in this case. Okay, so vj square is what the total force that is required by the firefighters to hold the this hose, actually hose pipe. Okay, so all these are some common applications that we see in day-to-day life. So if you keep on thinking, you can create a lot of situations like this. Okay, cart, okay, vane, whatever you see, all these things we can keep on creating this, but you know, we will stop at this point. So remaining whatever the things that comes out, we will use them in the equations. Okay, because this is not within this control volume. Okay, so the control volume, if you see, for example, if this is considered as a tank here, look, if this is considered as a tank here, so let us suppose from the large tank, of course I cannot draw the very big tank actually, but let us suppose if there is some large tank to which normally there will be some small opening to the hose actually, so the tank will be very large actually at this point. Okay, so whenever this tank is actually very large, whenever the tank is actually very large like this, okay, I'm drawing a small tank, but in actual case this tank will be very large. So if you take this as the complete control volume, then also this, there is no velocity with which the fluid actually comes into this system. Okay, whatever is the internal fluid is there, that is pumped with some high velocity, that's it. Okay, so that's why, like in the previous case, if you see, if you take this as the control volume, this system as the control volume, the force needed to hold this system is basically depends only on the outlet velocity. That's the reason. Okay, it's not neglected that we don't consider that basically. Okay, because externally there is no velocity inflow into the system. So let us go for this case of angular momentum. So I'm concluding this linear momentum case till this point. Okay, so let us go for the case of angular momentum. So one very famous example, let us talk about lawn sprinkler. Lawn sprinkler. Okay, so let us suppose if you have a lawn sprinkler, for example. So here, if you see this case, okay, so let us suppose this is the case. Let us suppose if you have your, pivot here, basically let us suppose if you have your sprinkler here, and let us suppose the entry is radial at this point. So let us suppose it is connected to some location. Okay, so let us suppose it is connected to some pipeline, for example. Okay, so whenever this is connected to some pipeline, fluid enters. So there is some discharge that actually enters this case. Now this discharge which is entering is actually splitting up like this. Okay, so let us suppose whenever there are only two parts, this discharge got splitted equally, for example. Okay, so let us understand this in this way. So let us suppose this is Q/2 and this is also Q/2. Now the fluid is coming in this direction, V1, V1, and let us suppose if this is going out in this direction, which is V2, for example, and let us suppose this direction is R1 from the center and this is R2 from this center. Okay, R2 is basically from this center. Clear? So R2 is basically from the center and this is the pivot about which this is rotating. Pivot. Okay, now let us see here in this case, if this is R1 and that's R2, so discharge got separated. Okay, now we know that net torque that's acting, because whenever the fluid is coming it has a momentum and it's also rotating, so it is basically the case in the angular momentum case. So if you see net torque that's acting in this case is m dot VR at the outlet, and of course relative velocity at the outlet, minus m dot V in the radial at inlet. Okay, so here it is relative velocity, it's not inlet velocity. Relative velocity is what we need, V relative times R at the inlet. Okay, now try to understand one thing. Here mass flow is directly given because discharge that is flowing is directly given to this. Okay, so whatever is the discharge that enters, same discharge will actually come. So if you see at the inlet, I just want to tell you one thing. Whenever this is the center of rotation, the fluid is coming in this direction. So we know the fluid is coming in this direction and this is the center of means basically the pivot about which the sprinkler is rotating. So can you tell me, whenever the fluid is coming in, if this is the center, what is the angular momentum of the fluid which is coming in? What is the angular momentum of the fluid which is coming in if the velocity is to the pivot? If this has a axial entry or the radial entry basically in this case, 0, correct? Because there is no radius for that velocity, correct? Of course the fluid coming like this has some momentum, but that momentum is passing to the center of rotation, or the basically what is this, moment pivot basically. Okay, so in such case this R inlet is actually 0 because fluid is entering at R is equal to 0 actually. Okay, so at R is equal to 0. Clear? So fluid is entering at R is equal to 0. So R inlet is equal to 0. Now this implies, see here. So let us suppose you are writing in the scalar components, because you know torque is about this perpendicular plane because it's a plane rotation, it's not in 3D. So let us suppose if you write it in scalar, like how we write force. So let us suppose if you write that sigma T, for example, because you know torque is applied about this particular axis because it's the plane of rotation. Okay, now if you see net torque acting on fluid is equal to, this is on fluid of course, net torque acting on fluid is equal to, now you see the outlet is coming in two parts, correct? So m dot is split into two parts, q by 2 and q by 2 for example. Okay, let us suppose if you write q1 and q2, let us suppose let us write for some general case, but normally whenever there are two portions it splits into two equal halves. Okay, so q2 and q1, and this is the total discharge which is coming q. Okay, now you see this, if you see for the first part rho q1, m dot 1 is rho q1 into relative velocity through this arm. So if you see this is the velocity, this is the velocity and this is the radial location r. So please tell me, if I want to write the relative velocity Vr1, look, the sprinkler, let us suppose if this is rotating in the counterclockwise sense. Okay, so let us suppose the sprinkler is actually rotating in counterclockwise sense. So let us suppose this is rotating in the counterclockwise sense. Okay, so sprinkler is actually rotating in this direction. So whenever sprinkler is rotating in the counterclockwise direction, definitely this arm will try to move at a velocity which is r1 times of omega, correct? So fluid is moving along this arm, and this arm itself means the body of the sprinkler is also moving in this direction with r1 omega velocity, r1 times omega velocity, because you know linear velocity of the particle is means linear velocity of this frame which is here is equal to r1 times of omega. Let us suppose if this is omega, or generally if they give you n, you know omega is equal to 2 pi n by 60, whatever out of these two, whatever is given you use omega. Now this is r1 omega, correct? Because when sprinkler is rotating at an angular velocity of omega, this linear velocity with which this frame actually comes out is also r1 omega. So can you please tell me what is the relative velocity at this section? Can you please tell me what is the relative velocity at this section? V1 is in this direction, r1 omega is also in the same direction. So whenever these two are in the same direction, whenever V1 is in the same direction and r1 omega is also in the same direction, what is the relative velocity? So type in the chat box. Normally this V1 is because of the flow. What happens? Okay, so there is some flow of the fluid, so the fluid comes out with some velocity. Okay, so this V1 is due to the normal flow of the fluid in this sprinkler, and this r1 omega is due to the rotation of the body. So please tell me, if these two are in the same direction, then what could be the relative velocity here? So this is V1 plus r1 omega. What you have written first is correct. Okay, so what you have written first is correct actually, V1 plus r1 omega. The reason is, I will tell you, this concept of same direction subtraction doesn't hold good in rotation because it is V1 plus. Okay, why? I will tell you. Look, plus is the correct answer, but why plus? Look, normally the fluid will try to come in this direction, correct? Because there is some velocity because of the flow. Since there is some flow of fluid, so the fluid will come out with some velocity V1. Now whenever this arm is also traveling in this direction, physically what happens is, of course, if you forget about this vectors and all, see what happens physically is, look, I am center of the sprinkler, this is my arm which is rotating like this. Okay, now whenever my arm is rotating, fluid is trying to come out from this end, and this arm is throwing the fluid with extra velocity. Understood physically what's happening? So the fluid is trying to come out in this direction, and this rotation is facilitating to throw this fluid with some excess velocity because of the centrifugal force that's present. Clear? So whenever the arm is rotating, the fluid which is here, it's trying to throw this effectively. Okay, so that's how the velocity is actually increasing. It's more than V1. Understood? Is this clear? Did you understand how this is plus sign? Because if you see, this sprinkler is effectively throwing the fluid which actually increases the fluid, okay, than the flow velocity. So that's why it is V1 plus r1 omega. Similarly here, relative velocity at this section 2 is equal to V2. Here also fluid is moving in this direction and this sprinkler arm is also moving in this direction. So again we have V2 plus R2 omega. We have this. Okay, so V2 plus R2 omega. So therefore Q1 times of at the outlet is split into two parts. So rho Q1 times of V relative velocity 1 of the first part, V1 plus R1 omega into R1 plus rho Q2 times of V2 plus R2 omega times R2 is what you have. Okay, so this is the net torque which is acting in this case. So net torque on fluid is equal to, so rho, if you take, okay, if you write normally, no issue. So rho Q1 times of V1 plus R1 omega times R1 plus rho Q2 times of V2 plus R2 omega times R2. So this is the total net torque which is acting on the fluid. So obviously on the sprinkler minus of that sign, that's it. Okay, so this is how we have the sprinkler case. So sometimes what they give you, they put both the arms in the same direction. Okay, so whenever this is in this direction, so fluid will try to come in this direction, but the sprinkler will try to move in the opposite direction. In that case, let us suppose if this arm is actually downwards like this, then V2 minus R2 omega comes. Okay, you might have understood why, because fluid will try to come in this direction, sprinkler will try to take it back. Okay, so that's how it's actually some decrease in the velocity, effective velocity. So we get a minus sign whenever this sprinkler is actually in this direction. Okay, so if you understand the concept, you can play with the plus and minus sign whenever the arms are located. Okay, so depending upon the direction of the arms, you have to just put the plus or minus sign little carefully, that's it. Okay, if that is known, then everything is very simple. Okay, but the concept is why velocity increases is because of the centrifugal action of the arm. Okay, so whenever this arm is rotating, it will try to throw the fluid much effectively, then that's the reason why this velocity actually increases. Clear? Because this is the case of a rotation actually. Fine, but normally in linear mechanics and all, whenever if both the velocities are in same direction, then definitely velocities will decrease. Okay, means difference of the velocities is the correct answer. Okay, but why there is plus is because of the centrifugal action of the arm. The arm will try to throw the fluid much effectively. Okay, so that happens here. Fine then. Okay, so if that's the case, then this is how we use the sprinklers actually. So if this arm is in this direction or if this arm is in this direction, depending on the rotations and all, we know we can have the things. Okay, so net torque, as long as there is net torque, the omega value keep on increasing, because actually what happens whenever there is some net torque acting, that net torque will try to produce some I alpha. Okay, let us suppose the sprinkler has some angular this about this axis. Let us suppose if it has some moment of inertia, we know tau is equal to I alpha for rigid bodies. So as long as there is some torque which is acted on the sprinkler, so definitely the sprinkler has certain moment of inertia, so there will be some alpha. So whenever there is alpha, omega value will increase actually. Okay, but at any particular instant, at the instant when omega is at some particular value, then this is the expression for the torque. If omega changes, then definitely total things changes. Okay, so we have one more case, but only some 3-4 minutes is left, so we will see that case after in the next session. So in the next session, we will try to see some good applications of Bernoulli's equations. Okay, basically it's Venturi meters, flow meters we'll see, basically Venturi meters, orifice meters. Okay, and flow nozzle meter, I'll just give you introduction. Pitot tubes we will see. Okay, so we will see all these things in the case. Okay, so we will define something called the stagnation point, which you might have seen sometimes. Okay, we will talk about all these things. Clear? So don't miss the session. We'll talk about a bit of Venturi meters and all. We'll talk about one small case of this sprinkler and all. Again, there is one case where the 3 arms for the sprinkler. We will talk about that, and then we will start these concepts of minor losses and also flow meters. Clear? Okay, so we'll meet at 9:30 again. So please join back at 9:30. Clear? I hope this is understandable to you. You all understood when to put a plus sign, when to put a minus sign, when to put this relative velocities, when to put normal velocities, all these things. Take care. Then please come back at 9:30. We will meet at 9:30, and then we will continue the session. Okay, we will see some good amount of flow nozzle meters, all these things, flow measuring devices basically. Okay, fine then. Thank you all. We'll meet at 9 o'clock. Sorry, 9:30. Okay, yeah, thank you all. Thank you. Bye. Take care. Come back at 9:30. We will continue the session. Thank you.